quinoline system will take up the electron, but I was wondering the phosphine ligand, they themselves are very good pi acceptor ligand, right? Can they
Yeah.
take up the electron?
No, no way. The reason is the phosphine, it can have 3 and 5 oxidation states, right? Okay. Now, if you look at this particular phosphine, which is having strongly electron donating group and attached to the ferrocene, it's a redox invariant. It's not redox active at all. Okay. And this particular group, if there is any redox active group, that is the iron center of ferrocene, right? So phosphine is completely invariant as far as the electron acceptance is concerned. So you have only one option, as because of the fact copper 1 cannot be reduced to copper 2. So quinine can easily be reduced. That's why I said only very few selective organic molecules which could be considered as redox active or redox non-innocent ligand. Is it clear?
Yes, yes, sir. But at the same time, I was wondering if Fe could take up the electron, perhaps.
No, 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 it cannot take up. Chemically also it cannot take up over here. If you look at this, phosphine is bonded through its lone pair, okay? And this particular phosphine is completely inert in terms of any redox transformation. So only option is the quinone one. Okay, I just, I think it is Harshavardhan, right?
Yes, yes, sir.
Yeah, I see very few attendance, okay? What is the total number of students?
Uh, I think the number is quite large, actually.
Hey, your voice is rather low. Can you be a little bit louder?
Yeah, I'm sorry. Is it better now, sir?
Yeah, much better.
Okay, okay. Yeah, I think the number is quite a lot. I think 70, 80 a minimum.
Students, total.
Yeah, yeah. So actually, what I feel is a lot of them are involved in these placement activities, at least the BS and the MS students. So
Okay,
maybe they are watching your lectures in recorded mode, is what I perceive.
okay, okay. But, that's why me and Prasad Datta was talking that listening and participating has its own impact
Yeah,
in,
I agree.
in terms of, anyway, it's an individual choice and online, we cannot, if it is offline, I could have called them. Okay. So, okay. So, can I begin now? Okay, now you are
Sure.
aware of it. The next Thursday we will take one quiz. Okay. And we will set the marks of 10 for that. And if we have difficulties in taking, your this online exam, etc., still we have to do it. I may convert it to 15 depending on the conditions. Okay, this is one issue, and second issue is that we have given some suggestions, and you have proposed something which I find to be more logical. But the problem is that I cannot, you cannot, draw anything, or you cannot use any symbols. It should be only objective. That is the difficulties I am having, but I will try my best. Okay, you
Uh,
Sir,
understand?
about the
sure.
recorded lectures, the lectures that are recorded and on the site are actually like have cuts where like in the middle of sentences. So like some of the lecture is lost in the like parts basically. Like one part ends at some point, but the next part starts a little later. Like this is happening. So can like cuts can be made a little shorter.
Okay, okay, but uh,
Okay,
now,
this is
now,
Arnav
now,
here. Sir, we will take a look into this matter and try to resolve it. We have the full lectures also. So we'll also try to upload the full lectures in the site.
okay, yeah. So we'll try to sort it out in due course of time, say tomorrow or something like that. And regarding the, this quiz, you can extend your suggestions if any further. We'll try to address it. Okay. Okay. Now let's come to today's talk. Now the today's talk, this particular topic, what I am going to talk about you, that would also answer the query. I think couple of days back you have raised that query. your that host guest techniques in ESR. And let me address this issue first. Then there are 2 points to understand out of it. One point, as you know, in one of the previous slides, I have talked about that metal ligand covalency, the concept beyond your crystal field, that is your ligand field concept. There we have shown this particular example. It suggests that metal nitrogen interactions in terms of MS and MI, and that gives the direct evidence in favor of your metal ligand covalency. Otherwise, this interaction would not, if the interaction, metal ligand interaction in the coordination sphere is only electrostatic, then this particular super hyperfine lines won't be resolved in the ESR spectrum. And that re-emphasizes the fact of covalency, and that also suggests the need of MO theory on top of your crystal field theory. When nothing was there, crystal field was very good. When crystal field was not there, VB was excellent. But this is how science grows, as a function of time. Now, this example would let you know both the aspects. One is that covalency factor. Other is that how the host guest chemistry functions. And also it would justify the fact of the JT effect in a serious way. Now, JT means John-Taylor effect. Now, if you look at this iridium compound, iridium in the +4 state, and all the ligands are same. And so you have 2 anions over here, which are being balanced, charge balanced by the 2 ammonium cation, mononegative cations. Now, since it is iridium 4, so naturally it's a D5. And since it is iridium, that means heavy metal, so it has to be low spin and is equal to half, the way it is shown over here. Now, this compound, it has a relaxation problem. Now, relaxation problem, as already we have talked about much before. One was that spin lattice relaxation, which is essentially controlled through the vibrational motion, and other one is the spin-spin interaction. Spin-spin interaction is basically induction or polarization effect, right? Induced magnetization effect. And we also said that in case of spin lattice relaxation, that could be largely controlled by lowering the temperature both in solid and solution states. And more particularly in solution state, it minimizes because of the Brownian motions, decreases, and all sort of things over there. Okay, so temperature control. And if you go for the spin-spin relaxation, and that's a magnetic polarization, right? Induction effect to the nearby magnetic center. So the only option to increase the distance between the 2 paramagnetic ions. One option to dilute in solution, but in the solid state, many occasions you may miss the EPR because of the relaxation, line broadening, followed by line broadening, followed by line vanishing. All 3 steps should take place. But magnetic dilution is possible in the solid state by considering a diamagnetic host. Now, diamagnetic host is not easy to get because here you have to make the solid solution. So you have to find out a host where the ligands are same, geometry is also same, where your almost everything is same except that one metal would be paramagnetic, other metal would be diamagnetic. One such host for this iridium compound is the analogous platinum compound. And if you look at it, is in the platinum 4 T6, again heavy metal, S equal to 0, and your geometry is absolutely fine. Okay. Now, these particular compound, they can be, and here you have to have the ammonium as your counter cation. Everything is same. Only one paramagnetic, other. So their crystal lattice is also same. And as a matter of fact, if you mix them, they would give you very homogeneous mixture in the solid state also, right? So for example, if you take one tris compound, and that tris compound, it could have your two geometries, we know, Meridonian and facial. So if you try to make a solid solution by using two facial sources, one diamagnetic, one paramagnetic, other parameters are same, only geometry is different, they won't give you the, solid solution. So you have to use facial to facial or meridional to meridional. But here that question does not arise, as because of the monodental ligand, all ligands are same. So only difference is the magnetic difference between platinum 4 and iridium 4. So as I already told you, at least 200, 1:200 ratio you have to use it, because EPR is a very sensitive. A pinch of paramagnetic site is there in a bulk sample, it would respond. So now if you measure the EPR of this ammonium compound, so and it's a very symmetric compound, na? With all axes it is same. And iridium and chlorine, iridium your I equal to 3/2 and chlorine I equal to 3/2, right? Now if you measure the EPR along any particular axis, you can fix the axis, I already said earlier, say x-axis, y-axis and z-axis. Then what will happen, your because of the 3/2, you will have 4 hyperfine splitting of the initial line, ms equal to half. And these 4 hyperfine lines will be further splitted 7 lines each. Thus, what is the source of this 7 line? Source is you have 2 chloride along one particular axis, and all axes are equivalent, right? X, Y, Z, 2 chloride, 2 chloride, 2 chloride. So 2 into 3/2 plus 1, so 7 lines. So that is being nicely reflected along X, Y and G axis. No problem. So there is not much JT effect over there. Okay, all axes are in interactive mode. But if you take the corresponding sodium salt, what do you see in X and Y axis? No, EPR profile is exactly the way it is being observed for the ammonium salt. But in the G axis, you see no super hyperfine because of MS and MI interaction for the chloride things. You only see the hyperfine 4 lines. Okay. What does it indicate? It indicates that it is nothing that tetracoordination. It is essentially hexacoordination. But along the G-axis, the distance is slightly, that means bond is slightly weaker, distance is slightly longer compared to X and Y axis. And as a result, it goes beyond the interacting mode. Interacting means MS and MI interacting mode. Okay. And if you record if you get the crystal structure of these 2 molecules, here you will see along the XY and G axis, MX, M chloride bond distance more or less same, are very close to each other. But here, along the plane, the distances are same, 4 distances, and across the G axis, your distances are different. That means 2 sets of distances, 4 distances in the plane same, and 2 distances, on the plane, it is essentially different. Just like the famous compound of JT effect, we know copper hexaco compound. Copper hexaco compound, if you remember, that was the first compound to establish the fact of the JT effect, where all ligands are same. One should anticipate same copper oxygen distance, copper 2 oxygen distance, but they have observed the 2 different distances. Here also the similar scenario. And even if we keep the X-ray aside, please, EPR could tell you very clearly that only in one direction there is no metal chloride interactions in terms of super hyperfine constant, and that is being nicely reflected over here. So it tells us 2 things. One thing, that covalency, that is how this interaction takes place. And second point, it says that in one case, your your JT effect is there. And then argument is why it is varying while moving from ammonium to sodium. And you will see the crystal packing is different. So how they are being packed in the solid state EPR, how they are being packed in the solid state, that is how everything governs or everything emerges. Okay. Now this is a very routine slide. You know that conventionally the hyperfine or super hyperfine constant, whatever we call in terms of A, that we define in terms of Gauss, right? The separation between the two lines in terms of x-axis magnetic field gap, right? This is the magnetic field, that gap in terms of Gauss or Tesla, whatever you want, that we define, okay? But it can also be represented very nicely. As we know, the h nu equal to g beta h. If you consider this h corresponds to this A, then it can be converted in the energy unit, centimeter inverse or megahertz, as like NMR. Okay. So just for your information, that for our convenience, commonly we define A and A means both hyperfine and super hyperfine coupling constant in terms of Gauss, but not necessarily you have to do all the time in Gauss. If you wish for certain purpose, you need the energy unit, right? Then you need to do, you can do in centimeter inverse or megahertz as well. Now, you could remember that we discussed this issue long back, that in EPR we can have that common X-band spectrometer, which is cheaper, which is good enough to serve our purpose in 90% sense, if not more. But there are certain occasions or certain cases where you need very specific informations. And that specific information you may not be able to get through your X-band EPR. So sometimes Q-band EPR, K-band EPR helps, but the high field EPR is very important, particularly those who are interested in doing the biological situation. For example, I'm giving you one example, that metalloproteins, if you take. Now, metalloproteins, we know that metal is inside the one particular macrocycle or one ligand environment, what we call in inorganic cells that one coordination situation, and the ligands are connected through big protein chains, right? Now, many occasions, it's not easy to crystallize the whole situation. And if you cannot crystallize, then you do not know the metal fragments, how it looks like over there exactly. Not only the donor centers around the metal, not only the geometry, but also their electronic situations, whether it is a distorted octahedral, distorted tetrahedral, distorted square planar, whatever it is, nothing you cannot get unless you crystallize that molecule and get the single crystal X-ray data. But conventionally, what people used to do, they used to go for XAF, okay, X-ray spectroscopic technique, and that could be done in solution also. So it gives a lot of information, proteins, etc. If you keep all these things aside, it gives some information which could be simulated or correlated to the bond parameters. Okay, that means what is the distance between the metal and ligand, and that X-ray would tell you whether the donor is sulfur, donor is nitrogen or oxygen. But in case of XAF, they cannot tell much. They can only show some electron density what you can correlate, but you can back calculate the ML distance. Now, it is certain that metal oxygen and metal nitrogen distance you cannot differentiate much. It should be very close to each other. But metal sulfur distance would be much longer all the time because of bigger size. Okay, so for example, I'm telling it. So you can have some impression through XR that what the donors could be. You can rule out that it is not sulfur, it could be oxygen. If you have some other prior informations. Okay, so but then if you want to understand their electronic situation, the normal EPR won't help you. So you need to go for the high field EPR. I just give you one example, you will understand how the high field EPR would help us to move in a better direction. For example, there are three spectra which are being plotted over here. Look at the situation. This is a 9 gigahertz machine. Okay, and this is a standard machine, and this is a very cheap machine, so 3 gigahertz. Now, if you record their EPR, the same compound using three different spectrometer in terms of their frequency behavior. Now, at 3 gigahertz instrument, it shows as a single line. Okay, but if you move to 9 gigahertz, the single lines could be converted into the two lines. That does mean that this frequency is not enough in terms of frequency and magnetic field ratio, is not enough to split this line, right? On the other hand, if you go to the 9 gigahertz with a particular magnetic field situation, this could be, resolved to two lines, right? With a particular A value. The gap you could see it, right? Using the same scale, if you go for, say, K band or Q band situation, where it is almost 30 gigahertz machine, you see the A increases. What does it mean? It means that if you have any super hyperfine or hyperfine splitting over here, let us assume super hyperfine, and let us consider this is hyperfine. Okay. Now, if super hyperfine, which cannot be properly resolved anyway, here also, even if it is resolved, which might have overlapped on each other and makes the system little bit less understood system. But if you have a situation like this, where both the lines are quite well resolved, so if you have any further splitting over here, chances are very less to miss them. So you could see them, you could simulate them, and you could get all finer details out of this spectrum. Now let us go to the situation. One particular compound, if you take this compound, already we have talked about, this is present in the nickel 1 in one bacteria which is called F430. Okay, it's a well-known bacteria. Now, if you look at it, is a nickel 1 means essentially D9. That means you have one unpaired electron in the EG set. And if you look at this geometry, is a square planar geometry. So we know that the top one, and it's already x square minus y square orbital, would have that unpaired electron because it is elongated. There is nothing along the g axis. So you should expect to have, in a standard fashion, one axial spectrum, where already we have talked about the g parallel would be greater than the g perpendicular. Okay, parallel means the smaller line. I have already explained earlier. It will be the smaller line, and perpendicular, it will be, intensity will be higher. And there what happened is 4 nitrogens which have created your 9 lines over here. And you see that there are 9 lines, but at a smaller level over here, which is not properly resolved. But here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 lines are there. Okay. But one question arises, is this compound truly truly axial, or it can have any rhombic feature? Now, rhombic feature would arise, I'll tell about it a little bit later on. If you have something attached to the nickel centers over here along the g-axis, and that could cause some kind of additional distortion in terms of geometry along the g-axis, right? So that feature is missing over here because if you look at the X-band spectrum, it appears as a single line, and that line has further been splitted by due to the 4 almost equivalent nitrogen centers, right? But if you go to 90 gigahertz machine, what do you see? You see essentially a rhombic pattern. That means I'll talk about it a little bit later on. That means X, Y, and Z, all the axes are now separated. That tells us very clearly that solvent molecules are somehow closer to the nickel center in terms of a kind of interactions over there. It is not really elongated. Okay, they are coming rather closer, and which is being reflected in the high field EPR in terms of fully anisotropic EPR feature. That means rhombic feature. Okay, and then if you go down to 4K, and slowly you'll be seeing all that spectrum I have not shown over here. You will be seeing that 9 lines over here. So you could realize what I'm trying to mean, that one particular nickel-based enzyme, and there you could see that nickel 1 unpaired electron, and apparently one could imagine that this is a square planar geometry because some kind of porphyric, not exactly it is porphyrin, it is actually reduced porphyrin. I think it is bacteriochlorine. Okay, so that kind of situation, if it is there, one should expect to have an axial situation where G-axis, there is no ligand. And if that axial situation is there, then you should expect to have this kind of bond, and then a superhyperion, which is nothing great, as expected. But some people thought from XR, there's some kind of nickel solvent interaction, they could feel it. But they could not establish that fact because there is no crystal structure. Okay, people could not solve the crystal structure in those days. And as a result, they went for the high field EPR, and they could see the rhombic feature. And that tells us the G-axis, some amount of MS-MI interaction, G-axis, some ligands are there, of course in a weak sense, not in a very strong sense. Okay, so this is how high field EPR is very, very helpful for certain reason. You need not to go for high field EPR all the time, and of course it is not possible. For example, in India there is no high field machine at all. Across the globe you will have only region wise. India use that France Grenouille machine, or you can use that Berlin. Of course there is one machine, and one machine is in if I am not wrong, that is in Brookhaven in USA. Okay,
So by high field you mean the going for Q band and W band, is that so, right?
No, Q band is not the high field. W band, the Q band is in principle it is much higher than your X band. We do have Q band over here. Okay, so I'm telling you the price wise Q band what we have over here, which is costing 4 crore. But if you go for 90 gigahertz machine, your cost would be 300 crore. Because magnet would be very big. You understood what I'm trying to say? And
yes.
The microwave generator would be also equally strong. So what I'm saying, the high field in a true sense, high field means you have to go 90 onwards. And Q band, it is around 30. Okay.
So I'm sorry, but I am still confused. What is the advantage of going for high field EPR? Could you kindly repeat?
Yeah. As I told you over here, initially it was thought that nickel is tetra-coordinated and it's a elongated system, right? Z-out situation. And under a Z-out situation, you should expect to have one line over here, G parallel, and G perpendicular over here. And G perpendicular has been splitted due to the 4 nitrogen equivalent they considered, equivalent 4 nitrogen splitting. Now, if you go for a high field EPR, because it tells you, because high field EPR means what? that your gap between the MS and MI, which that plus minus half in MS, you could remember the figure what I have shown some time back, which has opened up, right? So let me show you. Go back to that figure.
Yes, yes, the splitting diagram, right?
Yeah. Now the general splitting diagram. No, that would help you to understand what is the meaning of high field. Yeah, this is the diagram. Okay, so you see that splitting from here to here, for X band it is this much in terms of gigahertz, and now it is this much. So as a result, you need more H. That much of splitting would take place at a very high your magnetic field, and actually your required frequency would be much higher. And here what will happen, all sort of electronic distortion would be exposed of in a much better way. And that indeed happens in this particular case. As I said that, if you get the crystal structure, then you can prove whether any metal nickel solvent interaction is there at all or not. Okay. Now, if you do not have the X structure, then through XAP you can guess something, and they could get the sense that something is here along the G-axis. If you do not consider something over here, as far as the ligand and metal ligand interaction, then it's a perfectly square planar type of situation. And perfectly square planar type of situation is a Z-out situation, right? Tetragonally elongated situation. So you have a somewhat C4 axis over there. Okay, and then you can expect to have this kind of BPR, and that is being observed in the normal X-band case. But if you go for a high field DPR situation, then at a particular temperature, there you do not want to have this nitrogen hyperfine splitting in the beginning. Then you cannot get this splitting properly, and this tells you very clearly some kind of weak rhombic pattern. So weak rhombic pattern means X and Y, they are identical over here in terms of ligand field interactions, which has now been resolved. Okay, and you could see that X and Y are being splitted over here. And if you go further lower in terms of temperature, you will start seeing all these hyperfine lines along the axis. Okay, so it will tell you much better information about the electronic structural form of your compound. Now, in biology, this is extremely important, where you cannot have the structure, protein structures and all these things. Even if you get the protein structures, if you are interested in protein crystallography, you will see it's a food of error. Okay, people get some approximate information, how cytochrome C looks like, how this looks like, how that looks like. It's not a very precise structure like the small molecule what we do deal for conventional inorganic organic chemistry. It's a much bigger structure, right? And here it is just the cofactor. Okay, a lot of proteins are linked to this particular system, so you cannot crystallize it so easily unless you get a very precise structure. You cannot talk about their geometry. They only provide you the information. This is the general feature that at one corner your nickel is there. For example, if you look at your hemoglobin, okay, it's mostly the protein surrounded by, right? And somewhere small iron porphyrin units are there. Unless you have a very well-defined structure, how do you know that iron nitrogen, the porphyrin bond distance, iron is how far out of the plane? And then once you have all this information, then you need to try to understand what is the spin state of iron, deoxygenated form, oxygenated form, so on and so forth. So here one example I have taken. Here, if you want to know the exact structure over there, because this produces the hydrogen over there, okay, then it tells us from high field that it's not really axial. Some kind of weak interactions with the solvent molecules are there, and that is how you could get the separation of along the X and Y axis direction over here. Okay, so this is one example. There are many examples in the literature where you will see that hyphae leap year was used to understand the molecular behavior to a larger extent. But here the scope is very limited to speak. So I thought to give some impression to all of you. Okay. Now, when we talk about EPR, like chemical shift in NMR, okay, we define the electronic structure in terms of G. How the G varying from one compound to another compound, and why it varies. Okay. And also that hyperpoint, super hyperpoint constant, etc., etc. All sort of things would come into the picture. Now, the origin of G is very simple. Now, if we look at the very first few slides, where we said that the frequency what we need, h nu, which is a proportional equal to G beta h. So that means beta is a constant. You have two variant G and H. And if you use higher H, you need higher frequency, or vice versa. That's why the varying from X band to W band to Q band to W band, etc. Now, if this is the resonance condition, H nu equal to G beta H, then you can put all the values together and consider that H, which is the standard H for X band for a free radical. Free radical is close to the free electron. Na? Free electron is 2.0, and we consider free radical 2.0023 because of the relativistic corrections. We know that. Okay. So under the free radicals condition, where your G is conventionally, H is conventionally considered to be 3250 Gauss, then rest are all standard values, G would come to 2. Right? Now this G, from magnetic point of view, we can define it a little bit differently. Matter even same basically. Now, once you consider one electron in an orbit, we consider two types of motion, right? So along the orbital motion, what we call orbital magnetic moment, and the motion of the electron along its own axis. And that results in the spin motion, right? Now, for if we consider that simple orbital motion, then we know that mu L, already, we have studied all this thing, mu L equal to root over L into L plus 1 and G equal to 1. GL root over L into L plus 1. And GL we consider 1. Okay, why I am telling you. Next we consider the GS. If we simply consider the spin motion, then mu S would come, mu S equal to root over 4S into S plus 1, or conventionally root over N into N plus 2, N equal to number of unpaired electrons. We know all these things. And if we consider both ML and MS motions are there, but it is not so. Only spin motion is allowed, and orbital motion, mostly it is restricted in case of metal complexes. We know that. But let us assume for the time being that both are there. Then the equation mu L plus S equal to, we know that, root over L into L plus 1 plus 4S into S plus 1, right? But what happens, there we have considered the independent motion of L and S. And we have assumed that system behaves like way, that both the motions are independent and they are operational. But in practice, it may not be. Other option what we consider, based on the spin orbit coupling constant, if the spin orbit coupling is stronger, then L and S vector gives you the center J vector, right? And that is mostly operational, already we know it, in case of lanthanides, right? Lanthanide, mu L equation, mu S equation, mu L plus S equation won't be operational, only mu J equation is operational. Now, there we know that mu J equal to Gj root over J into J plus 1, but always unit is BM. BM, Bohr magneton, EH by 4 pi MC, right? Now, if we consider GJ, GJ is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2J into J plus 1. Now, if we assume that is the fact, in most of the cases, that L is not functional, orbital motion is being restricted by the Lagrange field. From crystal field concept, etc., we know it. And if you consider L equal to 2, sorry, L equal to 0, then J would be S, okay? So Gj for spin, it is 2. That 1 plus, this is S now, this is S, this would be S, this will be 0, right? So it is division of plus 1, so 1 plus 1, G equal to 2. So that is the origin of the G value, what we see in the EPR. EPR is the electron, right? Free electron. Okay. Here we are talking about free electron. That's why L we have considered 0. On the other hand, if you consider spin equal to 0, hypothetically spin cannot be 0, but hypothetically spin equal to 0, then this will be L, and that is how this will be 0. Okay, so GL would be 1. That's why for simple orbital motion gives you mu L equal to GL root over L into L plus 1 and GL equal to 1. From here we are getting so, right? So what I am trying to mean that for free electron G would be 2. But free electron is not the correct way to consider the molecule. The closest one is the organic molecule. Because here electron is not organic free radical I'm talking about. Here electron is not in a boundary conditions through the coordination axis, right? But that is why it is close to 2, but not 2 exactly because of the relativistics, it become 2.0023. That is the closest one, and in some cases 2.0036. 00 something. Okay. But in a metal complexes, where you have a particular geometry around the metal center, and metal is at the center of the geometry, either octahedron or tetrahedron or square planar or TBP, whatever you want to consider. And the electron is not free. It is confined to certain axis or certain geometry. So that restriction is there. And that would take it to some more additional interactions here and there. We'll talk it about. Okay. And that is why the values vary a lot. So what we have seen, the free radical G value is 2.00 something. Okay, X, Y, Z, whatever it is. But in a metal complexes, the G value, which is very much tunable by its geometry, and the values vary from 2.1 to 2.8, even 3. You have seen the 3G, even G10, G11, G, all sort of values are possible for metal complexes based on the geometry, based on electronic structure, and so on and so forth. Okay, so remember that thing. Now, you see that when we get one EPR, then we need to figure it out, even if it is a free radical, figure it out the G value. Now, how to figure it out the G value? You can figure it out by using one rider. Rider means that one free radical, which is a stable free radical under a particular conditions, and that G value is fixed. It does not vary much. So two riders commonly we used. We means across the globe. One called TCNE radical. So tetracyanoethylene, and here this is the common. This is not a radical. You have to reduce it, and then you will get one electron, say one radical, and that G value is fixed 2.0023. This radical is a very nice radical, but you have to put it in the seal tube. because on exposure to minimum amount of oxygen, it goes back to the initial neutral state, non-radical state. And you see that TCNE, it shows beautiful 9-line spectrum, which is natural. And this is 1, and then 4 nitrogen. So equivalent nitrogen 14. So it gives you 9-line spectrum. But if you use a small pinch, say 1 micro something, then you won't get the 9-line splitting, you will be getting a single line. Yeah? Now, another radical quite often we use, that is called DPPH radical. That means some names are there, diphenyl picric hydrazide radical. It's a complex but very stable radical. Here, unlike your, remember, unlike your TCNE radical, here it is stable. You need not to put it in the seal tube or vacuum. The reason is, a lot of, aryl rings are there and all sort of things. So it has a characteristic UV band, all sort of things. Okay. Now what happens that either you take TCNE or you take DPPH, it will have one, radical line, and you can also have the splitted line. But if you take a very small concentration in solid state, you will not get the splitting. Okay. Now, if you have this thing, and then what you can do, go back to the instrument for your understanding. The very beginning, I have shown you the instrument. Yeah. So here you have to put one tube where your compound will be. The tube has to be the quartz tube. You can see that quartz tube. If you use the glass tube, it absorbs the microwave. So you cannot use the glass. Very expensive. One quartz tube maybe $10. You cannot break it even. So you have to insert this tube within this magnetic field, and then you have to operate the instrument. And around that place, there is a small amount of solid TCNE or TCNE in a seal tube or DPP, you can keep it there. So during recording, what will happen, and your concentration will be very, very less. So what will happen, you will have your own spectrum, your own compound spectrum along with the TCNE or DPPH signal. And remember, TCNE is 2.0023 and DPPH is 2.0036, which is standard. So now what happens, say this is your compound spectrum, where your H is this one, right? At the center of the magnetic line, you consider this one the H, your, say H1, that is your compound H. And this is the place H for your radical one, standard one. So standard, you would see it here, the small signal, and that H you considered. So here for the rider, you know the G value, either 2.0023 or 2.0036 based on TCNE or DPPH respectively. And then you know H1 over here. And here your H2. Okay, that is your desired compound, unknown compound. And here your H2, but you only unknown factor is the G2. So you can simply apply G1 H1 equal to G2 H2, right? On the same frequency, you're using the same machine, same frequency. So G1 here you know, H1 you know, H2 for your unknown compound you know, but you do not know the G2. So G2 you will get it. Okay. Now how much it is different from the rider, that would tell you the location of the electron. Mechanically you can get it in the beginning itself. For example, let us assume that you have used DPPH, so 2.00, remember 36 or TCNE 23. Now after, once you get a spectrum of like this, isotropic spectrum, looks like a radical, may not be a radical, then if you calculate the G, instead of this, you may be getting 2.001. Once you get 2.00 something, that means that is radical. Whatever the profile looks like. But if it is 2.09, If it is 2.07, that means that is not a radical. You must have a metal complex where the electron is partially distributed at the interface of metal and ligand. It is shuttling between these two, mostly at the ligand, with a partial contribution at the metal site also. Okay, in the SOMO, what is singly occupied molecular orbital. Okay, it's not a unidimensional SOMO. It is not, if it is 2.00 something, SOMO is 100% composed of the radical. If it is 2.070609, that means you have 90%, roughly 90% radical composition at the SOMO, and at least 10% metal contribution is there. But if you get 2.1, the first digit, 2.1, 2.2, 2.3, that means you are slowly moving from radical to metal. So that means your metal participation in the SOMO progressively increasing from 10% in the previous case to, it could be 30, 40, 50, 60, 80, even 90, even 100 at one point, the purely metal-based signal. So what I am trying to convince you that G value is extremely important to assign the fact that your unoccupied molecular orbital, let us assume the singly, that is metal based or ligand based. Now I told you that conventionally that 99% ligand systems, okay, they don't exhibit much radical compound. They are mostly anionic or neutral. Okay, and in that case, if you have a transition metal based compound, and then you will see the G value is always 2.x, 2.1, 2.2, 2.3, whatever it is. So it is purely metal based. But a set of ligands, I said you quinones and few other ligands, their variable oxidation states are possible. They are called redox active ligand. And the frontier orbitals are those ligands, and the transition metals particularly, and their frontier orbital energy wise same. So electron can shuttle between the metal and ligand. And then the question comes up that what percentage of metal contribution, what percentage of ligand contribution in terms of electronic structural aspect of the molecule. And there, looking at the G value, if it is 0 something, that means you are essentially dealing with the radical setup. But if it is 2.0 something, that means some percentage of metal contribution is certainly there along with the dominating radical contribution. But if it is 2.x, that means 1, 2, 3, 4, whatever, that means you are primarily looking into progressive metal contribution, even up to 100% metal contribution without any ligand contribution. I hope I could convince you, right? Okay. Yeah.
If the value is less than 2, I think the transition metal case, you showed the range could be from 1.4 to 3, right?
Can you be bit, please louder a little bit?
Oh, I'm sorry, sir.
Yes, okay.
I think for the transition metal, the value of G could be 1.4 to 3 is what the range what you told, right?
No. It will be 2 plus.
Oh, always?
Yeah, always. It will be 2 to 2.1, 2.2, 2.3, all sort of things. Okay. And now what happened? Yeah, you are right. In certain cases, depending on certain factors, it could be close to 2, 1.99, 1.98. That could be possible. But generally, it is 2, greater than 2. And for free radical, it is purely free radical to 2.00 something. Okay, it could be 1.99, 1.98, 1.97 for free radical. Okay, but it only greater than 2. Understood?
Okay. Yes, sir. Yes, sir. And sir, could you repeat the wavelength graph in the previous slide? What was the wavelength graph about?
This is the DPPH, absorption spectrum. Okay, and if it is the pure DPPH, there is no absorption in the visual. There are, but nothing prominent band. But if you go for a radical state, you will be getting, and the color would be changed, and you will be getting beautiful absorption around 500 to 550 nanometer. It's a very characteristic band for the DPPH radical. Okay.
Okay. And in the right bottom, you showed na ki it could be less than 2.0036 if delta H is negative. So that's where I got confused.
No. It is showing that if you have your compound and your this thing, your rider together, okay, then how to differentiate it? The gap would tell you actually what it is. You understood? So what I'm trying to mean that if it is a free radical value either this one or 2.0023. Okay, but what we have noticed that normally it goes 2.00 something to even 1.99, 1.98, 1.97. There are many examples. But if you go for a metal system, the value would be 2.1 something. Okay, I'll show you. There is one more slide, and you will see that next one. Next slide, if you look at this slide.
Yes.
Okay,
Sir, can I ask one more question? I'm really sorry.
sure.
What is exactly rider? So you have been referring a lot in your
Oh, yeah,
statement.
rider means that you have to use one compound as a standard to calculate the G value.
Okay. So
You understood?
DPPH here, I guess, right?
DPPH or TCNE, whichever is available. TCNE is expensive, DPPH is not that expensive. And
Okay.
for example, in our system, we are using always TCNE, but in some other system, people use that DPPH. But remember, nowadays, I'm talking about something classical, the way we have grown, and you should also aware of it. Nowadays, instrument is so advanced. There is a Gauss meter is there, so which is fixed inside the instrument, and it tells you directly, okay, through some electronic measurement, because they also use some LiDAR, but that they don't expose it. So you will be getting your spectrum and directly the G value. You understood what I'm saying? And the A value. So
Okay.
instrument manipulates everything nowadays. But if, for example, the site machine, what we have, the EPR in the site, they use the TCNE till today. And the machine what we have in chemistry department, which is reasonably advanced machine, and their instrument, controls all these things, and there is no need of going into all these classical methods. But one must aware of it, how instrument does it.
Sure.
Even the advanced instrument, they follow the classical thing, but in such a secretive way that you don't realize it. Okay. Now if you go to the G value, what is the implication? I have already given you the impression that G value would tell you in a very simple or simplified system is the one electron system. I told you repeatedly that unless you have a diradical, EPR for organic molecule is not that difficult to follow. And that is true for NMR also. All of you know it. Organic molecules, organic people, they claim too many things, but I find it very simple. So with due respect to organic chemistry, so but if you go to the NMR of metal complexes, you would see how cumbersome and how difficult it is to assign. And I am 100% sure the organic chemist won't show their courage to interpret the NMR of your metal complexes. And forget about paramagnetic metal complexes. Okay, even diamagnetic metal complexes. Similarly, EPR for radical system or organic molecules, they are too trivial to me. Unless there are some exceptional cases already we have talked about in terms of benzyl radical and few other radicals we said. But the diradicals are difficult sometimes. But for a metal complex, once you have the G value, it tells you the location of the unpaired electron. And as I said to you very clearly, if it is in a conventional ligand system, it would be certainly mostly at the metal system, and G value would be 2.xyz whatever. Okay, more than 2. right? But if you have redox active ligands, then the question arises that primary location of the unpaired electron in the SOMO. There are three possibilities. One possibility fully at the ligand, fully at the metal, other two extreme, and intermediate description where partial disposition here or there, sometimes predominantly metal with minority ligand contribution, and sometimes the reverse, predominantly ligand with the minority metal or reverse one. Okay. Even if you consider a simple setup where we are not dealing with your redox active ligand, that and where it is expected that the unpaired electron would be onto the metal, and then also it gives us certain informations. Again, it comes back to the fact of that covalency. Okay, and that is how one terminology comes into the picture. You must have seen the orbital reduction factor. That is called K, small k. Now, small k from crystal field point of view, where it is considered the electrostatic interaction, it will be 1. Perfectly 1. If there is no covalency, covalency means metal ligand orbital mixing. Just electrostatic interaction, K would be 1. And if you have some amount of metal ligand overlapping, okay, then K would be progressively reducing from 1. Now, EPR would help us to understand this thing. Now, if you look at, read this slide little bit carefully, all the informations are over here. The G in a particular crystal field, the G value of a metal complex is essentially guided by several factors. The simple equation is 2, 1 minus alpha k square lambda 10 dq. Okay. Now, here lambda is the spin orbit coupling constant, which is listed in any book, any journal, everywhere you can pick up, which varies based on the size of the metal ion, which varies based on the charge of the metal ions in that compound. Alpha, it depends on the ground term. I'll talk about it. 10 dq, this information you will be getting out of your spectral absorption spectral feature. Okay, so only unknown factor over here, the EPR, you will be getting the G value, right? So only unknown factor is the K. K is the orbital reduction factor. Now, as I said, that what extent covalency persists over there in your desired compound or unknown compound through EPR with the help of other spectroscopic parameters or constant values, we can figure it out. For example, remember that this alpha values, it varies on whether the ground state is A or ground state is E or ground state is T, etc., etc. Now let us take two examples. Now, one example, nickel hexaaqua 2+. Now, nickel case, you know that water is not a redox active ligand. It has only one oxidation state. So there is no question of the second options of minority, majority, and all these things. Only options what you are looking out of this example, that how much covalency it is there over there. And covalency in the sense the metal ligand orbital overlapping is good or not so good from EPR perspective. Now, if you calculate this, your value is 0.9. I'll explain you how to calculate. 0.93. 0.93 means what? It tells us lesser than 1. That means it supports the ligand field theory. Because when ligand field theory came 50 years back into the market, it came through the physicist, right? And not through the inorganic chemist. And then there's a lot of debate between this thing, that what it was presumed that covalency, it is really so or not. Crystal field theory was far better. It was electrostatic, etc., etc. And then naturally, more and more spectroscopic technique came into the picture. EPR came much later on. And through this EPR technique, people have established very convincingly that what they did in terms of your MO theory, ligand field theory, that's the right and the best approach so far available. Okay, so if you look at this nickel compound, now you must remember the ground term of nickel is the 3F, right? and it's a D8 configuration, and 3F would be splitted into the three different ways. Na? We know all these things. I don't think we need to talk about it now. So then the ground term would be, this is the nickel configuration, ground term would be 3A2G. Na? Okay. And then this will be the 3F splitting profile. This is called crystal field splitting. Okay. Now 3A ground term, then 3T1, 322, and 122. These are all group theoretical terminology. Okay. So that depends on the symmetry and all sort of pattern. But if you keep that factor aside right now, then your essentially ground term spin multiplicity would remain same while splitting. Then why it is A? Do you know, or I should explain you? You could remember, I guess, right? Hello?
Yes, yes, yes. Yes,
Okay.
sir.
So then it will be 3A, 3T1, and then it is so. And then the lowest energy would be 3A to 3T1. Okay. So that is your this DQ, 10 DQ. That is a delta. Delta is the lowest absorption band from DD band I'm talking about. From here to, not the charge transfer band. And here you don't expect charge transfer because of the water. So from here to here, and that comes around 1100 nanometer, which is equal to almost 9,000 centimeter inverse. So 10 DQ is known. Nickel 2 octahedral geometry lambda is known from the book, and ground state is your A, alpha is 4. Okay, so if you put that in the equation, equation is here, 10 DQ known, lambda known, alpha known, and G is already known. G is 2.24, and then you will get the K value. Am I right? So 2.24, you can see it, 100% metal based thing. That's no debate, no doubt over here. But one information we are getting out of this K value, that here your covalency is there. But if you look at the next molecule, that is a similar situation, the copper hexaacue. Same copper and just same ligand water octahedral situation. But here your ground term is a 2D. We know how to calculate 2D. And 2D would be splitted into 2E and 2T. We know all these things. Why 2E? Because 1 ampere electron in 2 orbitals can be organized in 2 different ways. And then if you move this one, then 1 ampere electron can be organized in 3 different ways. So excited state is the 2T. And if you look at this absorption, which comes around 800 nanometer roughly, and then this is your centimeter unit of your 12,000 centimeter inverse, your lambda. Then if you put all the values, and it is E term, so alpha equal to 2 for E, 10 DQ known, lambda known, K is 0.69 by considering the G. Experimentally observed G is 2.13, and your K is 0.69. So what does it mean? That these two compounds are very identical, at least looking wise, right? Both are octahedron, both having same monooriented ligand, both the metals having same charge, but their electronic configuration is different. But their extent of metal ligand overlapping is drastically different. One is 0.9, of course, covalent system, but the other one is 0.69. That means, heavily covalent situation. So all sort of information we could get out of it, and we will talk about the other part later on. Other part means where you use the redox active ligand, the situation flips like anything. And there it's a just swimming in the ocean. Okay, but still we can have very reasonable interpretation through EPR and other techniques as well. So EPR alone cannot help you in many occasions, as I told you earlier, that particularly from inorganic point of view, synthesis is one of the important aspects. And after that, if you would like to have the electronic structural informations, you need to put various experimental details together along with calculations. Then only you can reach to a situation which is reasonably acceptable, if not fully acceptable. Okay. So now if you have the G parameters, then there are a few issues we need to understand with respect to not the electronic structure mostly, but the molecular structures. The molecular structure, I already talked about it. The molecular structure could also be nicely represented by the EPR profile. Okay, for example, if you have a fully octahedral situation, I'm not talking about the organic ligands. I'm talking about the metal complexes. A purely octahedral situation, if you take. And as I told you, in a chelated system, you will never expect to have the purely octahedral situation because of the chelate effect. You would be getting essentially distorted octahedral situation. But if you take monodentate ligand, like in the previous cases, nickel hexaacuro, copper hexaacuro, you are likely to have, at least in the solid state, where it cannot distinguish X, Y, and Z too much, and room temperature EPR profile would look like an isotropic situation where, like this, where Gx, Gy, Gz won't be resolved. You will be getting one absorption, and as a result, a derivative curve, you will be getting broad spectrum. Okay, one spectrum without any further resolution. Now, if you get this one spectrum, don't be confused with the free radical signal. If you calculate the G value at this point, you could easily distinguish the G would be much greater than the free radical G value 2.00 something to 2.1234 something, and that would tell you, keeping your eyes closed, you can say from the G value that this is certainly metal based. Okay, or somewhere in between. Now, if you have a situation, if you move from this situation to the solution situation, solution spectrum, and at your low temperature, where you can glassy conditions, where you would be expecting to get the maximum possible resolution, right? And then you can have two situations under tetragonally distorted situation. Already you have talked about your axial situation where G parallel, which is greater than G perpendicular, and other option is your compressed situation where G perpendicular would be greater than G parallel. Axial means that X equal to Y not equal to Z. Okay, X, Y, Z, which is a little bit, I should say, in a crude way to represent the situation, because in a bulk system, it doesn't matter much which one X, which one Y, which one Z, but you can consider three axes, right, which can be interchanged. But if you fix the single crystal for recording the EPR, you can define this is X, this is Y, this is Z. That's why the iridium examples, what you have talked about, where it was fixed in the one particular directions. But in a bulk, is a random. So essentially, you will be getting a situation where two G's are here. What happened? All three G's are equal. That means you cannot distinguish which corresponds to what. So you are getting one line spectrum, right? It's more random. But here it is partially random. So you will be getting Gx equal to Gy not equal to Gz, or any other combination, Gx not equal to Gy equal to Gz. Okay, so any combination is possible. Now, if it happens because of the, that means that what is happening along the G axis, you have the same ligand, and XY, Y axis, you have the different ligand. For example, metal tetrachloro dibromo. Okay, that means XY plane, if you assume the four ligands are identical, tetrachloro, and Z axis, you have two ligands, which is a bromo or water. So that means GZ is different. Now here we are talking about molecular or molecular structural behavior. That means G axis in terms of metal ligand interaction is different than the XY axis. Now if you change all the three axes, that means X axis say metal chloride, Y axis metal bromide, and G axis metal iodide. That means all three axes are different, and that would nicely be reflected in the EPR spectral profile. You see the GX, GY, GZ. Okay, and that means all are now being splitted. Here Gx not equal to Gy not equal to Gz, right? So you will have all four options in hand. One option is purely octahedral, absolutely isotropic spectral feature. Other option is tetragonally distorted setup, where you have two options. These are the two options. And the third and the fourth and the last option is gx not equal to gy not equal to gz. All axes are different. So you are essentially ending up to a situation what you call rhombic situations, or what you call also fully anisotropic situation. Now, under the circumstances, you can calculate the two parameters to define the anisotropic feature. One is called mode G. Mode G is essentially average G. For an isotropic signal, just 1 G could be the mode G. There is no second opinion. And here you have to calculate G1 with this formula, and G2 and G3 are same for axial situation. G2 or G3 same. Here also G2, G3, G1, whichever way you consider, they are same. And for a rhombic situation, you have a G1, G2, G3. G1, G2, G3. Once you have this experimental value, you put it and you will be getting the mode G. And then the value what you will be getting by using this formula, so 2.2234, 2.178, whatever it is, that value would you need to consider for further analysis or interpretation. And delta G, which is very well defined parameter and very effective parameters, delta G, forget about this one. This is the, it is not to have the spectrum in the best possible condition. So these two are the best possible resolution based on your molecular orbital situation or your geometrical situation, right? Axial or rhombic situation. But delta G means difference between the two extreme G from here to here, here to here, or here to here. This delta G, mode delta G means what is happening. That means mode metal character in a situation where both metal and ligand do have the opportunity to carry the unpaired spin. But if you have a compound like nickel hexaco, copper hexaco, and there you don't expect to have any spin, delocalization on the ligand side. But if you have a quinone system, nitrosyl system, azo system, there you have that possibility. But hypothetically, or in a very, what I should say, very routine way, I could tell that delta G tells you the mode delta G, which represents the metal character, less delta G, which represents your ligand character. For example, if you have a free radical, simple free radical, you will have sharp one line. So the gap would be basically virtually nothing. Okay, so delta G gap. So that's why it is said that for metal based, your G and delta G would be in a minimum way, I'm saying 2.1 or 0.25 from in a rhombic situation or axial situation from here to here. This is the minimum you can think about it, 2.1, 0.25. Whereas in a radical situation, you look at this mode G and delta G, 2 and 0.05. These are the two extreme. So you cannot, misjudge, right? There is no need of having any confusion. So if you have this kind of parameters from EPR, if you calculate this kind of parameters, that means you can keep your eyes 100% closed and tell, oh, it is metal based. But if you have this kind of situation, you can say ligand based. But if you have a situation in between, and that would arise only in the situation where you have redox active ligands along with the redox active metal in your molecular framework. Okay, then the difficult question is that what percentage of metal, what percentage of ligand they are contributing in defining the SOMO, singly occupied molecular orbital, and that needs to be addressed by a variety of techniques along with the necessary calculations. Okay, now what is the, I do have little bit time, na? Are you sure? Hello?
Yes, I think 5 minutes.
Yes,
from
sir.
now.
5 minutes, right? Very good. Now, This axial rhombicity, everything arises because of the fact of the orbital degeneracy. You already know about it, orbital degeneration. EPR is a reflection of orbital degeneracy. Okay. Now, for example, if you consider, say, iron 3 octahedral situation. Now, iron 3 means, and iron 3, I'm not considering high spin. High spin is a different scenario. Let us consider the low spin. Low spin iron 3 means, say, T2G5. Now, if you have a T2G5, that is essentially one electron setup, which is the simplest setup what we have been considering so far. Now, if you have a situation like this, that means X, Y, and Z based orbital, you cannot distinguish. That means one unpaired electron, your 2, 2, 1. So it could be here, it could be here, it could be here. And then you would be getting one axial situation. Sorry, one isotropic situation. As I said in the beginning, isotropic situation means this one. But the problem is, isotropic situation, which is absolutely impossible in a metal complex. Okay, because this degeneracy which leaps off, we know that, because of the ligand field effect. But that is still in a solid state, in the room temperature. Because of the technical limitations, you can have that kind of situation, but that G would be much different than the free radical G. So that's why that EPR won't provide you much information, and nobody looks for that kind of EPR profile. Okay, it's just like, many occasions you need to go down to the lower temperature to get the better NMR resolution. Nah? Okay, similarly. Now what happened if you have an axial symmetry? Axial symmetry means that out of 3 orbitals, 2 orbitals having the Z component. Axial symmetry means what? XY plane, that configuration would be same because of the same ligand field. Okay, and only the Z figure would be vary. That means we are not talking about any chelated system. Chelated system we cannot define that way. Nah? Only monodentate setup. If we, as I said, X and Y having the same ligand setup, so your ligand field varying along the z-axis. So that means the orbitals having z component, they would be different than the xy based orbital component energy wise. Now the pattern could be reversed also. Here I have shown one pattern. It could be this is lower, xy at the higher state. It doesn't matter. That means essentially what I said to you, that gx equal to gx not equal to gy equal to gz. But these two are identical. If they are identical like this, then you will have two lines in EPR. That is your tetragonally distorted system. Now, if this xz and yz, they again vary, that means the z is now different. Z, there are 3 types of ligand, AA, BB, CC. That means Z would also now differ. So here you have a situation V, that means weak rhombic situation, and this is a larger rhombic situation. So everything essentially depends on the difference in ligand field strength of the field strength of the ligand along the Cartesian axis in a particular metal complex. That's why you get isotropic, you get axial, you get rhombic situation. And the subsequent slide essentially showing the same thing. And isotropic, you can look at, this is axial situation. Within axial there are 2 variants, and it's a rhombic situation, right? Okay, this is the absorption mode, this is the derivative mode, and the same is being summarized over here. You can go through it. They are not talking, the slide is not talking anything new. What I have said, it is being shown over there. Now here the tetragonal situation, and this is called trigonal situation, we know already, na? Trigonal situation, not many variations, just you can have the rhombic pattern, and how much delta G variation depends on that means G1 minus G3, that variance which is depending on the fact of what kind of distortion you have along the X, Y and G axis based on the ligand field strength or chelate effect, all sort of factors are there. Now in a tetragonally system, we know that there are 2 situations. One is the elongated, G parallel, G perpendicular. Other is compressed, G perpendicular, G parallel. That depends on the fact, already I said many times, that these two orbitals disposition. If Z square is lower, that means your elongated situations. Okay, that means Z is unpaired electron is actually over here. Okay, so one unpaired electron is over here, and in this case, one unpaired electron is over here. That is Z compressed. Okay, and we already talked about that. Intensity at the parallel axis would be much lower compared to the perpendicular axis because of the fact of less number of ions would be along the perpendicular parallel axis of the magnetic field, and opposite direction would have maximum numbers of ions, so your intensity would be higher. So this already we have talked about. Now this is the same scenario in a copper case. You see that there are two lines, one because of this splitting, other because of this splitting. So G parallel, G perpendicular. The same story in a different way. Okay, so I think I should finish it over here. So this is how we talked about. So if we take our quiz on next Thursday, so I will have 2 more classes, and we will cover the rest of the items through our 2 classes, and then we will have exam, and exam. Let's see how much marks Muruga will covered, and rest of the marks I will be covering. So as far as the quiz is concerned, we will begin with 10 marks. And which format we need to follow, your suggestion is welcome. You have already given some good suggestions. We are trying to work on that. If you have any additional suggestion, please feel free to share by today or tomorrow, because you have to finalize it. And then you'll go for the end-sem exam with the remaining marks. And please go through the slides. And if you have any difficulties, feel free to contact me so that I can try to address your queries. Thank you very much.
Excuse me, sir.
Yeah. Yes.
Good afternoon, sir. What would be the syllabus for the quiz till today's class or the last lecture?
What do you want?
The last lecture, sir, please.
Hey, why not today? Because you have on Thursday, you have two more days are there in between.
But we have almost every quiz scheduled for this week. That's why.
Don't worry, yeah, because here the advantage is online. No, listen, online the advantage is I cannot ask very strong questions to you because you cannot draw. The way we are planning to do it would be more of objective.
Okay, sir.
And you cannot draw anything, you cannot use any, just I would like to get some information whether you could follow or not. That's it. So don't be worried about the quiz, just to learn it. That is more important. If you can learn something, which would be my pleasure. Okay.
Okay, sir. Thank you so much.
All the best.
Thank you.
Okay.
Okay, thanks for the lecture, sir.
Anybody else?